Carbide burrs, also known as carbide rotary files or burrs, are specialized cutting tools engineered for high-precision material removal in applications like cylinder head porting. These tools are primarily constructed from tungsten carbide, a composite material that combines tungsten and carbon atoms in a sintered matrix, often with a cobalt binder for added toughness. Tungsten carbide is renowned for its exceptional hardness, typically rating around 9 on the Mohs scale, or 1500 to 2000 on the Vickers hardness test, making it one of the hardest materials used in industrial tooling, surpassed only by diamonds and certain ceramics. This inherent toughness and durability allow carbide burrs to withstand high rotational speeds, resist wear, and maintain sharp cutting edges over extended use, far outperforming softer alternatives like high-speed steel burrs. Material removal process in cylinder head ports. Cylinder heads in internal combustion engines feature intake and exhaust ports, curved channels that guide air-fuel mixtures into the combustion chamber and expel exhaust gases out. These ports are typically cast from materials like aluminum, common in modern performance engines for its lightweight properties, or cast iron, used in older or heavy-duty applications for its strength and heat resistance. Over time, or in stock configurations, these ports may have rough surfaces, sharp edges, or restrictive geometries that impede airflow, reducing engine efficiency, power output, and throttle response. Carbide burrs efficiently remove material from these ports through a high-speed rotary cutting action. Here's a step-by-step breakdown of how this works. Tool setup and operation. Carbide burrs are mounted on a high-speed rotary tool, such as a pneumatic die grinder or electric Dremel-style tool, capable of spinning at 20,000 to 50,000 revolutions per minute. The burr's shank, the non-cutting end, fits securely into the tool's collet or chuck. The cutting head of the burr features a series of flutes or teeth arranged in patterns like single cut, straight flutes for smoother finishes, double cut, cross-hatched for aggressive material removal, or chip breaker designs to prevent clogging. These flutes act like miniature chisels, shearing away material as the burr rotates. Material interaction and cutting mechanism. When the spinning burr contacts the port surface, its tungsten carbide edges generate intense shear forces. The hardness of tungsten carbide allows it to penetrate and fracture the workpiece material at a microscopic level. For aluminum, which is relatively soft and ductile, Mohs hardness of about 2.5-3, the burr slices through with minimal resistance, producing fine chips or swarf that are evacuated via the flutes. In cast iron, which is harder, Mohs 4, 5, and more brittle, the burr's edges chip away material through a combination of abrasion and impact, breaking it into smaller particles. The cobalt binder in the carbide provides shock resistance, preventing the burr from fracturing under the intermittent loads encountered in cast iron's heterogeneous structure, which includes graphite flakes. Efficiency stems from the burr's ability to maintain edge sharpness. Unlike softer tools that dull quickly, carbide burrs resist thermal softening. They can handle temperatures up to 800 to 1000 degrees Celsius without losing hardness, and abrasive wear, allowing for sustained cutting without frequent replacements. This results in faster material removal rates, often 5-10 times quicker than manual filing or sanding, while generating less heat, which is crucial to avoid warping delicate aluminum heads. Precision shaping for airflow optimization. Precision is achieved through the variety of burr shapes and sizes available, such as cylindrical, for straight walls, ball-shaped, for rounding corners, flame or tree-shaped, for accessing curved or undercut areas, and tapered, for blending transitions. Operators can select the appropriate burr to target specific port features, like the valve guide boss, short turn radius, or bowl area beneath the valve seat. The process, known as porting and polishing, involves controlled material removal to reshape the ports. For instance, enlarging the port, using a coarse double-cut burr to hog out material, increasing the cross-sectional area to allow more airflow volume, measured in cubic feet per minute, or CFM. Smoothing surfaces, switching to finer single-cut burrs to eliminate casting imperfections, ridges, or flash, reducing boundary layer turbulence that drags on airflow. Reshaping geometry, carefully contouring the port's floor, roof, and walls to create a smoother velocity stack effect, minimizing eddies and promoting laminar flow. This can improve airflow by 10 to 30% or more, depending on the engine, leading to gains in horsepower and torque. The hardness of tungsten carbide ensures minimal tool deflection under load, enabling micron-level precision. Operators use techniques like light pressure and overlapping passes to avoid gouging, often guided by airflow bench testing, for example with a superflow bench, to verify improvements iteratively. Safety measures such as eye protection and dust extraction are essential due to the fine metal particles produced. In summary, the superior hardness and toughness of tungsten carbide make these burrs ideal for cutting through aluminum or cast iron with efficiency and control, transforming restrictive ports into high-flow pathways that enhance engine performance. You can order our carbide burrs on our website today to get 10% off.